Hello everyone, my name is Akshata and I am giving this video presentation for the 10th National Power Electronics Conference organized by IIT Bhubaneswar. The topic of my presentation is LLC Resonant Converter with wide output voltage range for USB power delivery. Now let us discuss the motivation behind this work. Use of portable electronics devices such as laptops, mobiles, speakers, and personal computers is increasing every year. And all these devices need a dedicated charger for powering up. So these chargers, once discarded, are producing huge e-waste every year, and hence there is a need of single output universal charger which can provide output voltage from 5 volt to 20 volt and up to 100 watt of power. The recently launched USB power delivery standard along with USB Type-C connector is a promising candidate to meet this requirement. Now let us look into the typical charger circuit which is available in the market. It consists of two stages, and the first stage is a power factor correction based boost converter, which controls and regulates the DC bus voltage and draws sinusoidal current from the grid. Now the second stage is a DC-DC converter, which regulates the DC output voltage, and the half-bridge LLC resonant converter is preferred due to its inherent soft switching capability, and it is suitable for high frequency and high power density application. Now let us look into the literature circuits which worked on improving the output voltage range of this conventional half-bridge LLC resonant converter. So the first circuit is the reconfigurable primary side structure. In this, there is a full bridge at primary, which can be reconfigured as half bridge by keeping switch S4 continuously on and S3 is turned off. So the full bridge configuration gives 20 volt at the output, and half bridge configuration gives 10 volt at the output. So we can get the 1:2 output voltage range with this circuit without deviating from the resonant frequency. However, in order to achieve the 4 times output voltage range, the switching frequency variation is very large, which deteriorates the performance of the converter. Now let us look into the reconfigurable transformer structure, where we get the 2 different output voltages depending upon the position of the switch S. So when switch S is at position 1, only N2 winding conducts, and when switch is at position 2, only N3 winding conducts. This gives us 2 different turns ratio of the transformer corresponding to 2 different output voltages. So with this configuration, it is possible to achieve the 4 times output voltage range with almost constant switching frequency. However, the number of devices in the conduction path are 4 in this case at the secondary, which increases the conduction loss of the converter. Now, let us look at another circuit, which is reconfigurable bridge circuit. In this circuit, it is possible to achieve the 3 different output voltages depending upon this conduction state of the switch S5 and S6. So these are 2 switches, S5 and S6 are the 4 quadrant switches, and when switch S5 is turned on, only N2 winding conducts. When switch S6 is turned on, only N3 winding conducts. And when both the switches are turned on, both the windings conduct, giving us the 3 different turns ratio. So it is possible to achieve the 4 times output voltage range with this converter as well. However, the number of devices in the conduction path at the secondary are 6, which further deteriorates the performance of the converter due to the increase in the conduction loss. Now, let us discuss the objective of the proposed circuit. The main objective is to obtain the 1:4 times output voltage range, that is 5 volt for mobile charging application and 20 volt for laptop charging. So this range to obtain this 4 times output voltage range with almost constant switching frequency, and the minimum number of devices should be in the conduction path on the secondary side. to reduce the conduction loss of this converter. So the proposed circuit topology is shown in the figure, where switch SA and SB operate at 50% duty ratio at resonant frequency. And this resonant frequency is determined by the resonant inductor and capacitor connected in series, which is given by this equation. And the circuit operates in two different modes, and that is the full bridge mode and voltage doubler mode. The mode of operation is determined by the conduction state of the switch S5. The switch S5 is a bidirectional or a four-quadrant switch, as shown in the figure. So when switch S5 is turned off, only N2 winding conducts, and all the switches in the secondary operate at resonant frequency with 50% duty cycle. And when switch S5 is turned on, then then only switch S1 and S2 operate at resonant frequency with 50% duty cycle, and both the windings N2 and N3 conducts. And switch S3 and S4 do not operate in entire switching cycle. Now let us look into the detailed operation of the full bridge mode. At t equals to 0, the switch SA is turned on, and LR resonates with CR, which gives us the sinusoidal ILR as shown in the graph. And the positive current flows through the secondary through switch S1 and S4. At time t1, ILR becomes equals to ILM, and switch SA is turned off. And due to positive ILR current, the parasitic capacitance of the switch SB starts discharging, and anti-parallel diode starts conducting. Since the ILR equals to ILM, there is no current in the secondary, and capacitors CO1 and CO2 provides the current to the load. At time t2, switch SB is turned on with 0 voltage switching, and LR resonates with CR with a negative ILR, and negative current flows through the secondary through switch S3 and S2. And at time t3, ILR again becomes equal to ILM, and at t3, switch SB is turned off, and due to the negative ILR, the parasitic capacitance of switch SA starts discharging, and anti-parallel diode starts conducting. Since ILR becomes equals to ILM, there is no current in the secondary. And again, the next cycle continues with where this switch SA is turned on with 0 voltage switching. Similarly, the operation of the voltage doubler mode can be explained. The only difference is that switch S3 and S4 do not switch and participate in the operation, and switch S5 is in a conduction state, and both the N2 and N3 winding conducts. Now these are the simulation results for the proposed circuit, where we can see that the output voltage for both the modes of operation has less than 1% of the voltage ripple. Circuit achieves both the output voltages, that is 4 times output voltage gain, without deviating too much from the resonant frequency. This is the power loss analysis of the converter, where we can see that the 50% of the overall losses are contributed due to the secondary conduction losses in full bridge mode, and almost 60% of the overall losses is contributed by the secondary conduction loss in the voltage doubler. So we can conclude that the major loss is due to the secondary side of conduction losses. So this is the efficiency, this is the graph of efficiency versus percentage output load, where we can see that we get overall higher efficiency at both the output voltages. Now let us discuss the quantitative comparison with the state of art circuits. So when we compare with the available circuits in the literature, the proposed circuits require only 2 primary side MOSFETs, 4 secondary side MOSFET, and only 1 auxiliary switch. And this gives 4 times output voltage gain range. And the number of with minimum number of devices in the conduction path, which is 3. And due to this, the efficiency of the converter is improved by almost 2.2% at 20 volt, and efficiency is improved by almost 5% at 5 volt compared to circuits available in the literature. So to conclude, we can say that the circuit is successfully providing the 4 terms output voltage, that is 5 volt and 20 volt, with moderate MOSFET counts, narrow switching frequency range, and higher overall converter efficiency. Also, the quantitative comparison of the proposed converter with the state-of-the-art circuit is provided. Further, the experimental verification of the proposed circuit can be done along with the integration of the USB PD control. With this, I appreciate for your valuable time, and thank you for patiently listening.